Today we are going to discuss about a composite material course of subject code MA 606101. This is a course for 6 semester students. So we are going to see today Unit 1, Introduction to Composite Materials. Composite materials can be defined as a combination of two or more materials that results in better properties than those of individual components used alone. The main advantages of composite materials are their higher strength and stiffness combined with low density when compared to bulk materials. There are two constituents in composite materials. They are a reinforcement and a matrix. These constituents retain their identities in the composite, that is, they do not dissolve or otherwise merge completely into each other, although they act in concert. Composites are one of the most widely used materials because of their adaptability to different situations and their relative ease of combination with other materials to serve specific purposes and exhibit desirable properties. First of all, we must know what is a matrix and what is a reinforcement. A matrix is also called as a binder. This is the continuous phase that surrounds the reinforcement and gives the material bulk form and transforms stress between the reinforcement. The common matrices include polymers, that means resins, metals and ceramics. The reinforcement means the discontinuous phase, typically in the form of fiber called glass fiber, carbon fiber and aramid, particles or flakes which provide strength, stiffness and other exceptional physical and mechanical properties to the matrix. The need for the composite materials. The primary reason for using composite materials is to achieve a combination of properties that is not possible with the conventional single material called metals or polymers and ceramics allows. The key benefits of this composite material needs driving their use include it's having superior strength to weight ratio. That means composite materials can be significantly lighter and stronger than the traditional material like steel or aluminium, which is crucial in application like aerospace and automotive industries for improved fuel efficiency and performance. And composite materials having good corrosion resistance, which do not rust or corrode, and making them for ideal marine, chemical and outdoor environments, which reduces maintenance cost and increase the product lifespan. And design flexibility. The composite materials having ability to tailor material properties by orienting fibers or choosing different matrix reinforcement combination allows for immense design freedom and the consolidation of many parts into one single complex component. And durability, fatigue resistance. The composite materials generally offer excellent resistance to fatigue, that means repeated loading, and impact, that means sudden loading, leading to a longer service life compared to many metals. And composite materials having good electrical and thermal insulations, which is beneficial for a specific application like railway infrastructure or fire protection. The advantages of composite materials lead to the widespread adaptation of composites in numerous industries, from everyday item like bathtubs and sporting goods to high performance applications such as aircraft fuelages, wind turbine blades and bulletproof vests. Composite materials are engineered to enhance properties such as strength, stiffness and durability beyond those of their individual component. They are primarily classified on their matrix material and form of their reinforcement. Enhancement of properties. Composite achieve unique combination of properties not typically found in conventional materials like metals, ceramic, polymers alone. The matrix phase is a continuous body that encapsulates the reinforcement, transfers the load and provides environmental protection that means corrosion resistance, while the reinforcement phase is typically stronger and stiffer, bearing most of the applied load. The heat enhanced properties, already we have seen high strength to weight ratio, corrosion and chemical resistance, tailored properties, improved fatigue and improved impact resistance, enhanced thermal performance. Now we are going to see the classification of composite materials. These composite materials are classified in two constituents, that means matrix and reinforcement. So matrices are polymer matrices, metal matrices, ceramic matrices, and carbon and graphite matrices. These polymer matrices can be classified into again two types. One is thermosets and another is thermoplastics. The example for thermosets are epoxy and polyester, and example for thermoplastics are polystyrene and nylons. And again, metal matrices are classified into alloys, that means steel and aluminium. Ceramics are again classified into three. One is glass, another is ceramics, that means semiconductors and cements, and cements. Organic or polymer matrix composites. Here are thermoplastics, already we have seen the examples. Here the classification of thermoplastics, again the polythene, polystyrene, polyamides, nylons, and polypropylene. Thermosets are epoxy, phenolic polyamide resins, and polyester. Thermosets have quality such as well bonded three-dimensional molecular structure. After curing, they decompose instead of melting or watering. Thermoplastics have one or two-dimensional molecular structure, and they tend to at an elevated temperature and show exaggerated melting point. Another advantage is that the process of softening and at elevated temperature can be reversed to regain its property during cooling for thermoplastics. Metal matrix composites. Metal matrix composites are high strength, fracture toughness, and stiffness are offered by metal matrices than those are offered by polymer counterparts. They can withstand elevated temperature in corrosive environment than polymer composites. And metal matrix composites are widely used in engineering applications where the operating temperature lies between 250 degrees C to 750 degrees C. Main matrix materials are steel, aluminium, titanium, copper, magnesium, and super alloys. And ceramic matrix composites. Ceramics can be described as a solid material which exhibit very strong ionic bonding in general, and few cases covalent bonding. High melting points, good corrosion resistance, stability at elevated temperatures, and high compressive strength are the advantages of ceramic composite materials. These ceramic composites are applied where the operating temperature lies between 800 degrees C to 1650 degrees C. Carbon and carbon matrix composites are developed specifically for the parts that must operate in extreme temperature range, composed of carbon matrix reinforced with carbon yarn fabric, 3D woven fabric, and 3D braiding, etc. The carbon matrix composites meet application ranging from rocket to aerospace because of their ability to maintain and even increase their structural property at extreme temperature. Advantages of these carbon matrix composites are used in highly elevated temperature called ranging from 1930 degrees C to 2760 degrees C, and having good strength at elevated temperature up to 1930 degrees C, high strength and stiffness, and good resistance to thermal shock because of its high temperature withstanding capacity. Function of a matrix. The matrix holds the fiber together, protects the fiber from the environment, distributes the load evenly between fibers so that all the fibers are subject to the same amount of strain, enhances transverse properties of laminates, improve impact and fracture resistance of a component, carry interlaminar shear. The desired properties that matrix should have are reduced moisture absorption, low shrinkage, low coefficient of thermal expansion, strength at high elevated temperature depending upon application, low temperature capability depending upon application, and excellent chemical resistance. The classification of composite materials are, and again reinforcement. So far we have seen matrix, now reinforcement. Reinforcement may be of fibers, viscous, laminar, flakes, filled particulates and microspheres. See the examples is given in figures. And fibers are maybe of short fiber, long fiber, plies, threads, organic and inorganic. And viscous are single crystal or multi crystals. Now we are going to see fiber reinforced epoxy composites. That means the fibers are the important class of reinforcement as they satisfy the desired conditions and transfer strength to the matrix constituents, influencing and enhancing the properties as desired. Laminar composites are found in as many combinations as the number of materials. They can be described as material comprising of layers of materials bonded together. These may be of several layers of two or more metal materials occurring alternately or in a determined order more than once and in as many numbers as required for specific purposes. Particulate reinforced composites. Microstructure of metal and ceramic composites which show particles of one phase swim in the other are known as particle reinforced composites. The square, triangle and round shapes of reinforcement are known, but the dimensions of all their sides are observed to be more or less equal. The size and volume concentration of the dispersed distinguish it from dispersal handled materials. Flake composites. Flake are often used in the place of fibers as can be densely packed metal flakes that are in close contact with each other in polymer matrices can conduct electricity or heat, while mica flakes and glass can resist both. Flakes are not expensive to produce and usually cost less than fibers. Filled composites. Fillers may be a main ingredient or an additional one in a composite. The filler particles may be irregular structure or have a precise geometrical shape like polyhedrons, short fibers or spheres. Fillers may be the main ingredient or an additional one in a composite. The filler may have irregular structures. Microspheres are considered to be some of the most useful fillers. Their specific gravity, stable particle size, strength and the controlled density to modify products without compromising on profitability or physical properties or their most sought after assets. Solid microspheres have relatively low density and therefore influence the commercial value and weight of the finished product. Studies have indicated that their inherent strength in carried out over the finished molded part of which they form a constituents. Hollow microspheres are essentially silicated based, made at controlled specific gravity. They are larger than solid glass spheres used in polymers and commercially supply in a wide range of particle size. The factors affecting the properties of composite: the type, distribution, size, shape, orientation and arrangement of the reinforcement will affect the properties of composite materials. See, first figure shows the distribution, second figure shows the concentration, third figure shows the orientation, fourth one shows the different shapes of fibers, and fifth one shows the different size of the fibers. Advantages of composite materials: light in weight and low density, high grip resistance, strength to weight ratio and stiffness to weight or greater than that of conventional materials like steel or aluminum, good fitting properties, it's not corrode easily, ease of fabrication of large complex structural shapes and modular construction, ability to incorporate sensors in the material to monitor and correct its performance, smart composites, high resistance to impact and improved corrosion resistance. The limitations: high cost of raw materials and fabrication. Composites are more brittle than the raw material and thus mostly more easily damaged. Transverse properties may be weak. Matrix is weak, therefore low toughness. Reuse and disposal may be difficult to attach, difficult with analysis. Cost can fluctuate. Application of the composite materials: glass fiber reinforced polymer composites are applied in the field of automotive and marine bodies, production of leaf springs, sporting goods, storage containers, industrial floorings, bathroom shower tubs and shafts. Whereas Arabic fiber reinforced composites are applied in bulletproof vests, pressure vessels, missile cases, automotive brakes and clutch linings, caskets and sports shoes. Similarly, carbon fiber reinforced polymer composites is applied in the making of golf sticks, fishing rods, aircraft and helicopter components and motor cases. And metal matrix, as far as aluminum matrix composite is reinforced alumina fibers are used in automotive connecting rods and pistons and aircraft wing panels. Copper matrix are used in propeller upshifts and titanium reinforced matrix are used in production of turbine blades and discs. And ceramic matrix composites, alumina reinforced with silicon carbide is used as a cutting tool. Inserts for machining core metal alloys used for high temperature application like gas turbine and ice engines. And rocket motors, brake discs of racing cars and aircrafts. Leading edge of aircraft airframe vehicles are produced by carbon-carbon composites. And hybrid composites are used in manufacturing fishing rods and 5-cycle beam made of glass carbon reinforced composites. Thank you. That's all.